talk about lenses and predicting the image location of a lens. And I'm going to start off with some definitions and show you what some things are so that we can kind of go from there. So first off, there are two types of lenses. One is a concave lens and one is a convex lens. And like we talked about with mirrors, a concave lens is one that bends. The way I look at it is it sort of caves in. So I call it concave because it sort of caves in. Convex bulges out. So here's a concave lens and here's a convex lens. Concave lens is on the left. Okay, this lenses work by way of refraction. So in the definition of a refraction is at the top of this page. And the refraction is the bending of a wave as it enters a new medium at an angle. So if you think about it, the ray of light that's leaving this object here, I'm going to call this object O, is going to be traveling to this lens, and it's going to be bent or refracted as it travels through this lens due to refraction. And that's because the velocity of light in the glass that the lens is made from, or the plastic that it's made from, is different from the velocity of light in the air. So that's refraction is going to occur, and it's going to occur at both of these surfaces, coming in and going out of the lens. Okay, and we're going to talk about that. Okay, so a concave lens, we'll talk about a concave lens first. It caves in. A concave lens is a diverging lens. Okay, and I'll show you what that means. Okay, and basically, so it's a diverging lens. I'm going to circle that down here. And basically what that means is that if you have some rays traveling, let's say I'm going to put 3 rays here traveling to this lens. And first of all, let me just explain a couple things before I do that. I have these 3 rays traveling like this, and I'll put another one. I'll put another one kind of here. What the heck, okay? And so I've got 3 rays traveling from this object toward the lens, and these rays are going to diverge when they hit the lens. Okay, this line through the middle of the lens is called the principal axis. I'll just label that P. Okay, that's the principal axis. Okay, this axis up here is called the normal axis, and it's normal or 90 degrees to the principal axis, and I'm just going to call that N. This is the normal axis, okay, for these lenses. Okay, so that's that. Okay, lenses have 2 focal points and 2 centers of curvature. And the 2 focal points for this lens are here and here. And the center of curvature is here and here. And the center of curvature is going to depend on how curved this lens is. Okay? The center of curvature is 2 times the focal length, 2f. Okay? The focal length is the distance from the vertex here to the focal point. Okay? So there's 2 of these, one on each side, one on the left, one on the right. They're the same distance apart from the vertex, and the center of curvature is twice the focal length. Okay, so that's basically, that's kind of the definitions that you need to think about when you look at these. Okay, so this is a diverging lens. So what that means is if I have a ray of light strikes this lens at an angle, it's going to diverge outward. So for example, the light here, well, because it goes through the vertex, it's going to go straight. But the light that strikes this lens here at this position is going to diverge outward, such that if you projected that ray backward, it would go through the focal point. Okay, and this is going to do the same thing. It's going to diverge outward, such that if you put it backward, it would go through the focal point. Okay, so you can see these diverge outward. They separate. Okay, they separate from each other on the right side of the lens, and so therefore they're diverging. Okay, now the opposite's true over here. I'm going to draw an object. I'm not going to use this object. I'm going to draw a different object. I'm going to draw an object right here. The opposite's true here. So here's the focal point, center of curvature, center of curvature. And I have 3 rays. One here. I'll have 3. We'll have one there, and we'll put another one there. Okay, these are going to, so a convex lens is a converging lens. So what happens to the rays as they pass through the lens is they converge on the focal point. So these will all come through and will converge right here at this focal point. Just like that. So they're converging. So these are all converge on the focal point. Okay? So this is converging lens. This is the diverging lens. Okay? This is converging. Okay, so let's go on. Okay, so this is the same two slides again, except I've taken off that material. So again, this is C, this is F. I'm going to start with the concave lens. This is a diverging lens. It has two focal points. It has two centers of curvature. Okay. Now, this is a diverging lens. So the focal point of this lens is on the left side of the lens. So the focal point is going, for this lens, it's going to be negative. Okay. This is the object. Okay. The distance, the DO, is the distance of the object to the vertex. This is DO. Okay, that's DO. Okay, okay, and that distance is going to be positive. Okay, the focal point, which is going to be on this side, the same side as the object, it's going to be negative. Okay, so these rules, what I'm showing you here, applies to all concave lenses. It applies to all concave lenses. Okay, so I'm going to draw two lines. Okay, and basically one of them, first one's going to be parallel to the principal axis. Here's the principal axis. Okay, I'm going to draw a line parallel to the principal. Here's a ray coming off the head of this object, and it's drawn to the principal axis here. And then I'm going to project it back. Oh, it's going to diverge outward. Okay, and if I project that back, that ray's projection is going to go through the focal point. Okay, then I'm going to draw another ray right from the head of this object, right through the vertex. And just like that. There we go. Okay, so the image that's created by this lens is going to be where these two lines intersect. It's going to be right here. And this is going to be the image, I. Okay, DI is going to be the distance from the image to the vertex. And that's this little distance right here. Okay, now DI, for the case of this, is on the same side as the object. So DI is going to be negative. Okay, DI is going to be negative. Okay, the object, by the way, is on the left of the lens. Okay, so what does this image look like? Well, it's smaller than the original object. It's upright, and it's on the same side as the object itself, so it can be projected on a screen, so it's virtual. Okay, so in this case, any object with you, if you have a concave lens and you have an object, okay, you always have the image it creates is always going to be smaller, upright, and virtual, or SUV. Okay, let's move on. So now we got a convex lens. There are three cases. Okay, there's a case where the object is located inside the focal point here. And then there are two more cases where it's located between the focal point and the center of curvature. And there's another case where it's located outside the center of curvature. Okay, we're going to go back to this one for a minute. Okay, this is the object. Okay, and so first off, to get this guy, we're going to draw a line parallel to the principal axis, P. It's the principal axis. We're going to line parallel to this, and this ray is going to project down to the focal point. Okay, it's going to project down to the focal point like that. Okay, there we go. Because this is a converging lens. All the rays that pass through it will converge at the focal point. Okay? Okay. The object, by the way, is on the left. Okay? The focal point is positive. It's on the right. It's on the opposite side from the object. Okay? And DO is positive. It's on the left side. Okay? This is a converging lens. Okay, so I draw one line like that, right? Then I draw a second line right through the vertex, just like I did in the first one. And that goes down like so. We notice something, these never converge, they diverge. So they'll never connect. They will never intersect. And where they intersect is where the image is going to be formed. So what I'm going to do is I'm going to extrapolate these backwards to where they converge. And my drawing isn't great, but it should work out. They converge back here somewhere, and the image is like where they intersect, sits back here somewhere, and this would be the image right there, I. Okay, and DI, this would be DO, the distance between the object and the vertex, and this would be DI, the distance between the image and the vertex. Okay, so this image is larger. Okay, it's upright. Okay, and again, it can't be projected on a screen because to project it on a screen, it has to be on the opposite side of the lens. So this is virtual. Okay, and the DI is negative. Okay, the DI is negative here. Okay, because it's on the same side as the object. And in this case, this is a larger, upright, and virtual image. Okay. Okay. Let's go to the last one. Last couple. So these are two more convex cases, just like the one we just talked about here, except the object has been moved. Here it's between C and F. Here it's outside of C. Remember, the convex lens is always a converging lens. So the object's on the left. The focal point, here's a focal point on this side. Here's C on this side. Here's a focal point on this side. Here's C on this side. The focal point is positive because it's on the opposite side of the object. And DO is also going to be positive. And this is a converging lens. Okay? Okay? The last one is the same. The objects, well, let's come back to that. Let's do that in a minute. Okay, so we got that all done. So let's draw the rays. So we got a ray here. Well, the first ray we're going to draw is going to be parallel to the principal axis and then down to the focal point, like that. Okay, and the next one is going to be right through the vertex. And you notice they converge down here somewhere. And where they converge is where the image is formed. And there it is. And the head of the image is right there. This is the image. Okay, so for this guy, the image is larger than the original object. It's inverted, it's upside down. Okay, and you could project this image on the screen. Okay, this image is real. Okay, this image is real. Okay, okay, there you go. Okay, this is kind of how a movie would work. Okay, in other words, this would be the film, and this would be the screen. Okay, the DI here is going to be positive. Okay, DI is going to be positive. Okay, and so how do you look at this? Larger inverted real? Well, larger inverted real, it's going to be RIL. That's the abbreviation. Okay, so last one, we've got an object that's on the left. We've got a focal point that's positive, it's on the right. We got a DO that's positive, and we got a convex lens, so it's converging. Okay, and first off, so we got all that. So let's draw the last one. I'll draw a line that's parallel to the principal axis and down to the focal point. Whoops, I do that one not very good. There we go. And then I'm going to draw a line right through the vertex, like that. Bam. And here's my image. Okay, and my image is going to be like out here somewhere. Okay, so in this case, I didn't draw this really great, but the image is smaller, it's inverted, and it's real. okay? And DI is going to be positive, okay? And this is going to be SIR. This is going to be smaller, inverted, and real, okay? So based on this graphical method, I'm able to actually predict where the images will be located, okay? And I know this is kind of difficult and it's kind of hard to follow, but at least it gives you an idea how you can look at a lens and how you can predict where to find the image.